The MSV design uses multiple supply voltages for the core logic. The MSV methodology assigns high supply voltages to the timing critical path of the design and low supply voltages to the non-critical path. A design using power shutoff (PSO) implementation is a design of which some of the portions can be switched on and off as needed to save the dynamic and leakage power. As you can see in this block diagram, the various voltage islands have been made, and the corresponding power domain is assigned to them. Out of these, some of the power domains contain the PSO implementation, and hence they can be switched off when required. As seen in multiple supply voltage MSV designs, you have various voltage islands. Here also, in the blocks, the voltage levels are 0.8, 1.0, 1.2. So if you are going with MSV design, there are some constraints that you need to specify. You need to define power domains and voltage levels since different voltage levels exist. You also have to define level shifters and plan which domains can be shut off, power up, and power down sequences. You need logic to isolate propagation of floating signals from shutdown regions, registers to retain the state during the shutdown, and power and ground nets and switches. Reducing voltage levels reduces power and speed, but architectural planning and implementation methodology support is required. So how do we determine the lowest voltage levels that can be used to achieve frequency targets? How can we verify the implementation of the voltage domains, level shifters, etc.? And also, how can we meet our time to market schedule while doing this? So when you are using multiple supply voltage for your design, there are certain challenges that you need to take care of and plan its implementation. Because it affects synthesis, DFT, floor planning, placement and clock tree, even equivalence checking and structural checking. Power shutoff is a methodology where you disconnect or shut off power to a certain part of the design when that is not in use. So the best way to reduce power is to shut it off. It shuts off all switching activity for that particular part and virtually eliminates leakage power. But the challenges which are associated with power shutoff methodology are we need to figure out which portion or design part can be shut off. Also, you need to functionally verify power off and power up down sequences. We must ensure that shutoff logic does not propagate bad or wrong unknown signals. Also, the design needs to quickly recover without resetting the shutoff blocks. That is, we need to route through state retention power. Power shutoff methodology affects the architecture and all the design creation steps. It also affects all functional verification tasks, DFT and ATPG, placement, routing, and SI. Let's discuss some of the features of top-down MSV synthesis flow. You have multiple voltage domains and corresponding libraries are assigned to these domains and corresponding blocks are assigned to these domains. As you can see in this diagram, you have VDD1, which corresponds to 0.8 volts, and Lib1 is associated with that. With VDD2, you have 1.0 volt and Lib2 and Lib3 are associated. VDD3 is at 1.2 volts with a Lib4 association. Now, you can do top-down analysis and optimization and assign various blocks to these corresponding voltage islands. After that, you can do the incremental what-if analysis of your design with these voltage domains, and then you can insert the level shifters. After that, you can transfer the voltage domains and shift the information to the back-end tools like place and route and low-power functional verification.